begin.
Yeah, that would be smart.
So, last time. First of all, we figured out the area under curve f of x on AB was equal to something that we, in notational, we call the integral from A to B of f of x dx. This is called the definite integral from A to B, just finding the area under the function on the integral A to B. We saw this was the limit of Riemann sums. Basically, created a bunch of rectangles that live underneath the formula. And according to some modality, we did the right-hand rule, the left-hand rule, and the midpoint rule. If you take a limit as n approaches infinity, where n is the number of rectangles, you end up with the exact area under the curve, which we denoted to be this. We also, that was one of the main things we looked at last time. We also noticed that if f of x is an, because it's not unique, antiderivative of the function f of x, then, and of course f of x here we're assuming to be continuous, then it turns out that this guy we could compute by plugging in the upper limit into the antiderivative and subtracting the lower limit into the antiderivative, and this was called the fundamental theorem of calculus. It has two parts. This is part one. Part two, according to some people, just to point that out. But it comes in it's a theorem that comes in two parts, which basically tells you that the finding areas and finding derivatives, they're connected, they're linked, they're almost like doing reverse processes. Not exactly the reverse, because if you took a derivative and then you try to take the antiderivative, you lost some information, you lost a constant that may have been there. But we do know this fact is true. That the area under a curve, we can actually talk about it in terms of antiderivatives. We also, last time, spoke about the indefinite integral. Which is basically, you have this guy, where no limits are given, but in general we sort of think of that as the antiderivative of our function plus a constant. Okay. So it's almost like we're getting a formula in order to find the area under the curve, but the limits aren't yet specified. So that's kind of where we left off last time. So the idea is when we take this guy, is sort of reversing the derivative. Right? And I say sort of because there's a plus c, so you might not get back the exact function, but you get back something that's pretty close. And in some contexts, the plus c doesn't even matter, like in this context, because if you subtract one minus the other, the constants are going to die anyway. So when you're finding exact areas, the fact that you're off by a constant won't matter, but in general, we have this is true. And given more information, we can actually find plus c for some function. So if I know the antiderivative of a function and I happen to know a point that it passes through, then I could use these two to figure out the plus c if necessary. But this is called the general antiderivative of the function f of x. And so that's where we kind of left off. And so the idea is, now we're going to talk more about this, reversing the derivative. And we did that for one of our formulas. We're just going to do that for all of the basic formulas. To compute this guy, the idea is to reverse the derivative formulas. This leads to some, I'll call them basic rules. It's not what they're called, but there are some basic rules that we now know because we're reversing formulas. So for example, I know 1, the antiderivative of x to the n dx, this is going to be x to the n plus 1 over n plus 1 plus c if my n is not equal to minus 1. This is called the power rule for integrals. So we had a power rule for derivatives, there's also the power rule for integrals. Okay? So the idea is, you might have realized that all I'm doing is trying to reverse that rule that we did for derivatives. If I were to take the derivative of x to the n, I would bring down the old power and subtract 1 from the power. Here I'm literally doing the opposite. I'm adding 1 back to the power so I get the old power back, and then I'm dividing by that power to kill the thing that I multiplied by before. So the idea is we're just reversing the derivative rules. So in essence, every time I give you a derivative rule, I was actually giving you an integration rule in reverse. So every derivative rule you can even think of as a rule for integration, there's just a plus c that brings you back to the other way. So in that sense, let's deal with the case if n equals minus 1. Because notice here, n cannot be minus 1 because I would divide by 0. But if n is equal to minus 1, notice that means that we're looking at x to the minus 1, which I can think of as 1 over x. That leads to this rule. What is the antiderivative of 1 over x?
ln x.
ln x, right? Because if you differentiate ln, you get 1 over x, so the reverse is also true. In fact, we can make it a little more general. You'll notice that you put the x in absolute values. It actually works for both. Because our x here can be negative or positive, you can show that in both the negative and the positive case it will work. And I can show you here. You know that ln of x is just, basically it's ln x if x is positive, it's ln of minus x if x is negative, and so if you were to take the derivative of this, in the top case you just get 1 over x by our definition, and in the bottom case you get the derivative over the thing itself, it actually equals 1 over x again. So whether we're dealing with a positive or negative, we get the same answer. So this is the general antiderivative, ln of absolute value of x. It's actually important to have the absolute values. Okay? But again, the main idea comes from, we're just thinking about what function did I have to differentiate to get 1 over x? The answer was ln x. We can also talk about e to the x. Yes. What function do I differentiate e to the x to get e to the x? E to the x, its derivative is itself. The difference is here there's a plus c, and yes, the plus c's are also important when you're doing antiderivatives. So we have these basic rules. So now, and you might be asking, are there any basic rules that have to do with like the product rule, the quotient rule, the chain rule, all that stuff? And the answer is yes, but we're not going to cover it. Those are things you cover in a Calc 2 class. We will look at one called substitution, which is basically us reversing the chain rule. But in general, you'd have these 3 basic rules, and I'll give you some more once we talk about substitution. So let's actually do some examples. Oh, I did tell you about it. I thought I would have waited, but I did. We do have another rule. I think I was going to derive it, but let's just get derived. Derivative of a to the x. Integral of a to the x is going to be a to the x divided by ln a. And you can realize, because if I take the derivative of this, I multiply the thing by ln a, and so the derivative just divides by ln a. We can only do this because it's a constant. Let's do some examples. We're going to find the integral of all of these guys. A, B, C, D. H. I. By the way, these are reversing integration rules. This is just, it's something we know now. Like, you have to memorize these. Like, we now know this. You kind of always knew it, but in the other way. But this is just something we know now, and we're going to use it based on the different kind of examples. So the idea is, again, the rules are your templates. They tell you what to do. So the idea is, if you're given something, you try to make that thing fit the template and follow what the rule says. Right? You can talk about all the theory behind it that you want, but at the end of the day, you need to solve a problem. You need to know how to do that. So let's just go through these. A. Which rule do we use? Power rule. It looks like x to a constant power. So what does the rule say? Add 1 to the power, divide by the new power. As long as the power is not minus 1, that works. And so this would be x cubed over 3 plus c. That's the answer. Because it's the power. By the way, you can note if you differentiated x cubed over 3 plus c, the answer would be x squared. Okay, so you can always check your answer. It's one of those things where you can always check your answer. If you did an integral and you want to know, is that the right answer? You can always just differentiate your answer. You should get the thing back that you started with. Yeah, that's basically it. Do it again. X cubed. Dx.
X to the 4 over 4 plus c.
Plus c. Very important to have the plus c. There are no limits. We're doing limits in the last two examples, but that's basically it. Not so bad, right? They're like, he's coming with something. I don't trust this dude. I can't trust Javon. It's never that easy. It's never that easy. Okay, let's make something a little harder. C.
2/3 x to the 3/2 plus c.
Exactly. Why? You see a radical, you know your basic rules. There are no radicals in the rule. So the first step would be to rewrite it without using a radical. That becomes x to the half. Now it looks like the power rule. That's x to the n. You add 1 to the power and divide by the new power. This becomes x to the 3/2 over 3/2. But dividing by a fraction is the same as multiplying by its reciprocal, so that's just 3/2 x to the 2/3 x to the 3/2 plus c. about yeah?
Is the x on the bottom really x to the negative 1? If you multiply.
It is x to the negative 1, yeah.
So would you move it up and distribute?
Sure. I mean, I think it's easier to just divide it into each. We'd say one term denominator, divide it into each. And so this is just 1 plus 1 over x. And we're reversing derivatives, so it makes sense that this integral of a sum is the sum of the integrals. You can also think of this as you're adding up the errors under two curves. You can look at the error under the whole curve, or you can add it in pieces, you'll get the same answer. But 1 is an interesting number. What would be the antiderivative of 1?
X.
X. You can realize that because if I differentiate x, I get 1. That's the one way to look at it. You can also think of it as 1 is x to the 0. And then you add 1 to the power, you get x to the 1 divided by 1. So a couple ways you can get to that. But yeah, you can always use your intuition about what did I differentiate to get this number and kind of reverse it. 1 over x? I line up the absolute value. So it's just you following the formulas. So it's going to E. Okay, how do we do that?
2/3 x to the 3/2.
Give me the steps.
Rewrite.
Rewrite. Again, we're using our rules. We have to make these things look like rules if possible. There are no radicals in our rules, so we rewrite as the half power, this guy. 3x to the minus 2 x. Right, so I didn't actually do anything yet, I just rewrote the thing, so this is exactly equal. Now I can apply my integral rules. You can do each one separately. And so this we kind of did already. So that's x to the 3 over 2 times 2/3 plus here it's minus 2 plus 1 over minus 2 plus 1. So that would be plus 3x minus 1. Minus. F. Okay, what do we do here?
Can you leave the 3 e to the x?
Huh?
Can you just leave the 3 e to the x?
Okay, and what about the other guy?
You bring up the x to the 3rd.
It's minus 3. Antiderivative of this?
3.
This itself, right? Because you differentiate 3 to the x, you get 3 to the x. The constant won't matter. You can sort of leave it and do the integral on the function, just like with derivatives. Here, I'm going to add 1 to the power, gives us a minus 2, divided by the new power, which is a minus 2. So this is 3e to the x plus 7 over 2 is minus 2.
Isn't that a negative?
Where?
I don't know.
Because it's negative, I bet negative, I get positive. A common mistake here is that students will sometimes, because they think 3 plus 1, they put like a minus 4. Watch out for that mistake. It's It's minus 3 plus 1, you get minus 2. But then whenever you're in a rush, sometimes you make all sorts of silly mistakes. So that's one to look out for. How about G? G is a definite integral. You notice that G has numbers on it.
So it's antiderivative of the whole upper limit minus the lower limit.
Right, we use a fundamental theorem of calculus. Here, we have a definite integral. We need FTC, which means we're going to use the fact that this guy here is equal to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. By the way, there's a notation that we use for this. So let me just introduce that here. You say this is the antiderivative, and you write a bar with a little a here and a little b here. Bar is on the right side. It's just a straight bar. You put a and b. And then you remember plug in the top number minus plug in the bottom number. And so that's how we kind of write it. So this is notation here. So when you write that notation, I'll know that you should be using the fundamental theorem of calculus here, and then the result will be this according to that theorem. So in this example, you'd have the antiderivative from 0 to 1 of x squared dx. That is equal to, we actually did this in the first example, I believe. So we know that that's x cubed over 3. I don't put a plus c because there are numbers on this. Instead, I put a bar here, and I put a 0 and a 1. And then what I do is I take a 1 and I plug into the function, minus, parentheses, take a 0, plug into the function. And so the answer there is 1/3. Let's take a pause here. Interpret 1/3. What does that mean here? The fact that I did this antiderivative, I got 1/3 as the answer. What is that saying? The integral from 0 to 1 of x squared is 1/3. What am I saying when I say that? Yeah?
Is it the area under the curve of x squared is 1/3?
It's the area, right? Notice that this, remember what that meant. It meant the area under the function f of x between a and b on that integral. So when I say the integral of x squared from 0 to 1 is 1/3, what I'm actually saying is, if I look at y equals x squared, and I can choose whatever units I want for the x and y axis, but because this will work, and I look at from 0 to 1, and I look at the area under that curve, turns out that area will be 1/3. Now we can approximate that using the right-hand rule, left-hand rule, midpoint rule, using a finite number of integrals. We'll never actually get the number 1/3, but the more rectangles we use, we'll get closer and closer and closer to 1/3. And in the case that we theoretically use an infinite number of rectangles, 1/3 would actually be the answer that we head towards.
I have a question about f. So how did you get 7x to the negative third?
Because 1 over x cubed is x to the minus 3.
Oh. that's 3. I thought that was 5 up there.
Oh, no, that's a 3.
Yeah.
It's like, how did that 5?
Yeah.
Okay. Yeah, that would be confusing. It was a 3. So whenever you're finding a definite integral, you're finding an area under a curve. By the way, I think this is as good a point as any, is that at the beginning of this lecture when I said area under the curve, I actually put the word under in quotations. I don't know if you noticed or not, but I did. And basically when we say f of x dx equals the area under f of x on a b, specifically we mean the net area. Because remember how we defined our rectangles. Our rectangles were defined based on the y values of our function. The height of the rectangle was when we plugged in the x value into the function, that gave us the height of the rectangle. So the question is, what if your function was negative? You plug that x value, you would get a negative number, right? So what this kind of does for you is it gives you a rectangle. So let's say your function is doing this and it dips below here at some point, and again, you start to dissect things. You realize that doing the right hand, for example, right hand, you'll get rectangles where the heights are negative. So what you get down here is you get a negative area. Right, the value you get is negative, and that doesn't mean that there's such a thing as negative area. It just means there's a part of the area that's under the x-axis. And so, if, for example, if this is A to B here, and so you want to compute that area, what you'll realize is in this case, what the integral actually gives you is not necessarily the area bounded by the curve, but rather this guy will actually give you the area of one thing minus the area of the other thing. So if this I call A1, and that's the area of the first part, this is A2, the area of the second part. The way we set this guy up using the function as giving the heights of our rectangles, we'll get negative values here, and so that will give us a negative area. And so if I just take this integral over this interval, it'll give me a negative area here and a positive area here, and it'll actually cancel things out. And so that's why it's really the net area. And so that's a better way to think of it specifically. If you did want to find the actual area that's bounded in between these two, then you'll have to first of all recognize that the function goes underneath, and you'd have to just split these up, and you treat this as a positive number and compute the area, if you really care about space. But yeah, that's something you kind of have to look out for. I don't think I'll give you a problem where you kind of need to figure that out, but problems like that might be in the homework, and it's kind of something you should know in general. Just wanted to mention that. But yeah, in this case, your x squared is always on top, so you really have the area under the curve that's above the x-axis here. That's not a net area, that gives you the actual area. Let's get through the other two. What example am I on to? H. So again, a definite integral. And in theory, there's nothing different about this. I just want to show you a couple examples. I will expect you to be able to compute things like this, but also You should know how to interpret them in terms of areas. So this guy again, use this as a division, confuse yourself. 3 just a half e to the x, it's just a constant times e to the x. So what we do is we integrate that, just get a half e to the x, plus, integrate this, you get x cubed over 3, write that bar, 1 to 3. Plug in the 3 for the x's everywhere. Here you'll notice that the parentheses are actually pretty important. Minus parentheses, plug in the 1 for x everywhere. So that becomes 1/2 e cubed plus 9 minus 1/2 e plus a third. But you can write that. You can add the 9 and the 1/3. So 9 is 27 over 3, so that's 28 over 3. So I can have 1/2 e cubed minus e plus 28 over 3. So you apply your antiderivative rules just as usual, except when you have numbers here. Take the top number, plug it in, minus, open parentheses, take the bottom number, plug it in. And this is going to be the result.
Why in the parentheses is it minus 1/3, not plus 1/3? Because aren't you just plugging 1?
Yes, it should be plus.
So that changes the value.
So this would be minus, and so this is 26, right?
Yeah. That's 26 over 3, right?
Yes, that's a 3.
Yeah.
Yeah, from the 1/3. It's 27 over 3 minus 1 over 3, 26 over 3. What about this one?
Can you bring up the x?
Sure, but why? We'll have this. So I know I can't use a power rule because the power rule says it doesn't work for equals minus 1.
You can leave it on the bottom and have it be 3 times 1 over x.
Yeah, you can think of this as this is just 3 times 1 over x. That's a constant. We do have a rule for 1 over x. So this becomes what?
3
ln x, absolute values. It's 1, 4. So I get ln of 4 minus 3 times ln of 1. What's log of 1? 0. Log of 1 is always 0. So the answer here is 3 ln. Since 4 is always positive, you can remove the absolute values here, but just keep them just to be safe. It's not wrong to write it. But if you don't write it when you need it, it will be wrong. Of course, things won't always be this easy. I knew it! I knew it was going to come, so I knew it! This kind of segues into 5.4. Now we're going to talk about substitution.
So is that 5.3?
Yeah, 5.2 was when we did the fundamental theorem of calculus, and this is also in 5.2. Yeah. So 5.1 was when we did the right-hand rule. 5.2 is the fundamental theorem of calculus, which includes this. 5.3 is area under curves. 5.4 is 5.3 area under curves.
Yes.
No, area under curves is actually chapter 6. But this is the next one. So, substitution is essentially the reverse of the chain rule. But we for our purposes, we can essentially think of it as some technique we can use when the basic rules don't apply. So we have those basic rules, the power rules, e to the x, integral of e to the x, integral of 1 over x, all that stuff. And if we can actually, if we're given some expression, we can kind of rewrite it to fit one of these rules, and then we can actually find the answer that way. But what if you have something that you can't rewrite to fix one of these rules? Right? Then you use substitution. Now, in theory, this is how we reverse the chain rule, but we're going to use that as a technique to simplify integrals and compute them. The idea. You want to compute the integral of f of x dx. I'll give you an example next time. So what we're going to do is why it's called substitution is we're going to substitute an expression for a single variable. Customarily, u would be the variable. So a lot of students refer to this as u substitution because u is normally the letter used, but you can do it with any variable other than the variable you started with, essentially. The goal is to make f of x dx simple, i.e. make it fit a basic rule by changing the variable. 2, you must accomplish 2 things. One, let's make the function simpler. 2, its derivative must be a factor elsewhere in the function. If off by a constant factor, we don't care, we can factor it out. description is going to be confusing when I'm writing it down, but when I execute a problem, you'll see where I'm using each of these steps. The idea is when I take the derivative, it might be off by a constant factor, but I can always factor constants out. We know that works for derivatives, so we don't have to worry about if it's off by a constant factor. So really the variable part of the derivative should be somewhere else in the function. So it should make the function simpler, and its derivative should be somewhere else in the function. That's how you know you chose a good thing for you. If it doesn't fulfill these two qualities, that was a bad choice. Choose something else. 3. You're going to substitute. Into the original. Compute the resulting integral. Which should be easier in theory. If you do it right, it should be easier. And 4, because you change a variable, you always have to change it back to the original variable. That's called back substitute. Right, in terms of the original variable. So that's kind of the process for substitution. You're given an integral, it's complicated, you don't know how to do it according to the basic rules. So what you do is you substitute an expression for a single variable. That should have 2 consequences. One is going to simplify the function for you in this new variable. And by simple, I mean you can apply a basic rule to it. 2, its derivative needs to be somewhere else in the function because we're going to need to find the dx, the derivative of this function. 3, you substitute all this stuff that you found earlier into the original. It's going to simplify that integral, something you can actually do. And then once you get to the answer, you back substitute. So let me show you an example. Let's say this is what I need. Now that guy looks complicated. Not complicated in the sense that the function is complicated. It's complicated in the sense that I do not have a rule that looks like this. Can we simplify this to look like a rule?
You substitute b for 1 plus x.
No, I mean using algebra, but without substitution. Right? So again, and some of you forgot all the blasphemies that I mentioned from a long time ago in the test. I saw a lot of people canceling across sums and all sorts of craziness. But resist the temptation to just think you can take the radical of this and the radical of that, which I saw someone do something similar to that in the test. That would be the wrong thing to do. So you can't take the radical of this, radical of that, and then distribute that. Oh, it's the power rule. That is wrong. It is a radical. It does not distribute across a sum. You cannot simplify this to look like the power rule. Right? Not with any normal laws of algebra anyway. However, you kind of get the sense that, of course, this thing is what makes it complicated. That 1 plus x squared. If that thing was just x, that would just be x to the half, and then I could actually use the power rule. I could just multiply these and get the power rule. So you're like, wouldn't it be nice if that thing was just one variable? So that's why I'm going to substitute that one variable. That part makes it complicated, so I'm going to say, okay, choose u equals this guy. So I took the complicated part of our function and I substituted it with a single variable because otherwise I cannot simplify this. The radical doesn't distribute across the sum. Now, how do I know that I actually have a good substitution? Is that now I want to take derivatives. So if I take the derivative of u with respect to x, that will give me 2x. Okay. Now, remember I said we don't necessarily care about the constant, but the x part. Do you see that somewhere else in the function? It is right there. It's very important that it's somewhere else in the function because we're going to be swapping things out. This equation tells us that our du is going to be 2x dx. Right? Or in other words, there are a couple ways we can do this. Probably the way that I found, I never really did it this way, but in experience from teaching and tutoring a lot of people, a lot of students like doing it this way, is that they choose to solve for the dx. So they'll divide both sides by 2x. Yeah, I know, right? Okay. And now what this does, you'll realize, is that what you can actually do at this point is you can take all this thing you have here and you can swap it into the original, right? I can replace this expression here with just u. My dx I can replace with 2 du over 2x. The x in the bottom is going to cancel this guy. I'm going to have a new integral and u is going to be the only variable present. So step one was choose u. Always choose yourself. Okay. The second step, that was deep. Okay. The second step is to substitute. Alright, so you need to make sure that all the stipulations are fulfilled. The variable part is somewhere else in the function, that's good. Now you're going to swap everyone out. Right? So I didn't change x here. I know that my u, the parts that are important is the u, and I know what my dx becomes. I'm just going to plug those guys in, substitute them in. So the x is here, I didn't do anything with it, but what's under the radical is now my u. And my dx is not dx anymore, my dx is now this expression. du over 2x. And so now let's actually simplify that, which now we can. We have a product of things, cancellation laws apply, I can cancel the x's. There's a division by 2 here, but that's just a constant, I can literally just factor it out. So I end up with that integral. Now compared to the original integral, that one is actually a lot simpler. Why is it simpler? Because I have a basic rule that deals with that case. That looks like a variable to a constant power. So it means I can apply the power rule. Right? Before I could not do that. But by making this substitution, I changed the variable into some other variable called u, which was a lot simpler. The fact that its derivative was somewhere else in the function allows me to swap everyone out and not have any x's left over. So that was the point of that. But now it results in us getting a new integral that has a much simpler formula, simpler in the sense that I have a rule that deals with that case. And so now I can integrate. In this case, the power rule applies. So I have u to the 3 over 2 over 3 over 2. Or in other words, that becomes 1/3 u to the 3 over 2 plus c. 4, back substitute. So this is actually the answer. I just found the antiderivative. The problem is, here I gave you the answer in terms of u, but I was asked the question in terms of x. So that's not good enough. So basically, we have to finish up by replacing this u with the function of x that it corresponds to. And we, of course, realize over here that our u is 1 plus x squared. So I'm just going to go back here and plug that in.
So the du just becomes a plus c? Or
The what?
the du goes where?
What do you mean?
Because you have, when you take the
This expression means take the antiderivative of u to the 1/2. which is this.
Okay. So why did we substitute the 2x dx then? Or was that for later?
Having this is what allowed me to cancel that x, so that the x is in here. I need everything in one variable, right? Because if I have x's and u's mixed up, that's even worse. Like I have two variables now, what do I do with it? Right? The fact that the derivative was somewhere else in the function allows me to kill all the other, the variables that make everything messy. And so I only have this expression with respect to u. This expression, I mean, you can essentially think of it as like x integral of x to the half. Right? It's just like now the variable is u. So you can apply the power rule, and that gives you the antiderivative of that. Right? And so now our u was 1 plus x squared to the 3 halves plus c. And that's the answer. And you can realize that if you differentiated that, you actually get this. You can check, right? To differentiate this, you'd use the chain rule. The 3/2 comes down, the 3's cancel, you're left with a half. Subtract 1 from the power, you get a half power. That gives you this radical expression. But then you have to multiply by the derivative of the inside, which is 2x. Then the 2 cancel the 2 that was left over here, and you just have an x left on the outside.
All right, good luck, dude.
So the derivative of this is the original. This is the antiderivative. But the idea is, the expression was very complicated in the beginning, so we needed to simplify it. Simplifying with algebra wouldn't work. There's no way to actually make that radical behave because it's over a sum. So what I do is, the sum makes it complicated, replace the sum. Turns out that that was the right thing to do because the derivative of that sum was somewhere else in the function. That allows me to change this integral into one with a whole new variable. And the idea is, it's supposed to be simpler. I have a rule that applies directly to that case. So I apply the rule. I would get my answer in terms of u. But since they asked me a question in terms of x, I replace my u with the function of x. And that's your answer. That's the antiderivative. So that would be the answer. And you can check by differentiation that that's actually the antiderivative. And you'll notice that to differentiate here, I had to apply the chain rule. So the substitution, kind of by extension, is a way to reverse the chain rule. Let's do another example. It is something you have to get used to. You have to do a bunch of homework problems. Let's see. Substitution. How about this? What do you think?
Would the u be the 1 plus tx or the whole thing?
Right. The thing we did last time where we kind of divide each into the thing, we can't do here because there's a sum in the denominator. You can't split up the sum in the denominator. That's something that we should know. So basically the denominator is what's making it complicated. So I just go, okay, let's do u equals 1 plus e to the x. Let's find the derivative. My derivative would be, derivative of this is e to the x. then what I can do is I can solve for the dx. So du divided by e to the x equals dx. And now I can actually substitute. So my e to the x stays over this guy replaced with u, and my dx is replaced with du over e to the x. This cancels. I end up with the integral of 1 over u du. We know how to integrate that. It's element of u plus c. And so now I just have to replace that with what my expression is. That should be the answer. Similarly here, very complicated because there's a radical in the denominator and it has two things under it. Having those two things makes it complicated, so I decided to substitute that. Here my du, you'll realize, is minus 1 dx. So there's no other variable, so it's okay that I didn't get a variable here. So that means this minus du is going to be my dx. So basically, we have an integral 1 over the radical of u times minus 1 du. Or in other words, you can factor out that negative sign and rewrite this as u to the minus 1/2. And I can just apply the rules here. Add 1 to the power, u to the 1/2, divided by 1/2, same as multiplying by 2. So that would be the answer. And so now I replace my u with the expression. Do a similar thing here. The denominator makes it complicated, so let's replace that with a single expression. U is equal to 2x dx. Meaning that du over 2x is equal to dx. Go to the original and just start plugging these guys in. So that's 3x over u. My dx becomes du over 2x. The x's will cancel. And I have now 3 over 2 that I can factor out. This leaves us again with 1 over u du. Very simple integral. I can apply a basic rule here. This is 3 over 2 times ln of u plus c, which is 3 over 2 ln of 5 plus x squared plus c. So we'll stop there. And I'll see you guys on Friday.
So what is exactly is 3 homeworks?
5.1, 2, and 4.
Yeah.
But I worry about studying for the test mostly.
Yeah, because I'll get back. Okay, so don't do it. Because we just have double tests.
Huh?
So when are the homeworks?
Like that, like 2.
By the last class.
So the second.
Yeah. But I would not do the homework. Like, you need to do enough so that you're comfortable with what you're doing.
Oh, yeah.
Oh, yes, I forgot. Okay.
Yeah, I'm like looking at it like